templateless, surfactant-free, and seedless approach to the single crystalline zinc oxide nanowires. I'm working under the guidance of Professor Wagner in Jammu University as a PhD student. As my friend told about the utilization and applications of zinc oxide, it's due to its wide band gap in large excitant binding energy. It's widely used in optoelectronic devices, transparent electrodes, photonic devices, transducers, biosensors, chemical sensors, and gas sensors. Nowadays, people are trying in hydrogen storage, photovoltaics, and catalysis. As I told that, my topic of today's discussion is surfactant-free and seedless aqueous route to a single crystalline zinc oxide nanostructures, zinc oxide nanowires. So the question is that, what makes this solution route so enthusiastic? In our laboratory, we are working on at the same time on COD, and this for the synthesis of SAM zinc oxide nanomaterial. People used MOCVD, MB, laser deposition for the one-dimensional nanowires, because the one-dimensional nanowires have much more properties and widely used in electronic and photonic devices. We use this aqueous solution route because of some prestigious advantages which makes expedient chemistry. We didn't use any, this work is entitled as surfactant-less and a template-less and seedless approach. The fabrication possible at large scale. There is low cost and low reaction temperature. The simple growth techniques, less hazards, no metal catalyst is used, and environmentally banned. Why nanowires? The Charles Leber, world's famous chemist, says that they represent the smallest dimensions of efficient transport of electrons and excitons, thus will be used as interconnects in critical devices in nanoelectronic and nano-optoelectronic. General attributes and desired properties of nanowires. They have the diameter less than 100 nanometers, single crystal formations, common crystallographic orientation along the nanowire axis, minimal defects, structural defects is minimal, and the minimal irregularities within the nanowire arrays. Experimental. We synthesized this zinc oxide nanowires using a single step of reaction, we can say the 1-pore synthesis, just using the HMT as a hexamethylene and HMT hexamethylene and the zinc source that zinc nitrate. The initial pH of the reaction is just a mild acidic, 5 to 6, and we stir 1 to 20 minutes and just refluxing at between the temperature of 50 to 100 degrees. And we did some experiments on time dependent. And finally, the product is centrifuged and vacuum dried for several hours to obtain. Further, we did the SEM observations to check the growth after 12 hours of reaction as previously described. We find some inorganic nanoparticles after 12 hours of growth of reaction. Further, when we increase the temperature up to 16 hours, we find some nanowires. So it makes our experiment much more interesting that there is a possibility to get these nanoparticles self-oriented themselves by a favorite mechanism of orientation attachment. So there is a possibility of enhancing prolong the reaction time. So there is a formation of nanowires. So further, when we increase the reaction time, we find a bundle of nanowires, and with this energetic nanoparticles within having the internal energy. So further, when we increase the reaction time to 24 hours, we find very good results with less than 50 nanometers nanowires. By first time, we are reporting this by a simple solution chemistry, very low temperature below 100 degrees. So further, this final sample which we fabricated at 24 hours, we did some FESM analysis. We find that the straightness of the this nanowires and the diameter is less than 50 nanometers, about 25 nanometers and 30 nanometers. In the range, so generally we say that below 30 nanometers, below 50 nanometers. So this FSM image shows the nanomorphology and shape. We did the EVS spectrum of zinc oxide nanowire bundle on large scale to check. We find that this zinc oxide nanowire is completely composed of zinc oxygen, and here a platinum peaks appears due to the coating of the FSM grade before the examination of FSM. Further, we check the crystallinity to see the crystal structure of zinc oxide. We did the XRD examination. We find that 101 direction is the growth axis is dominant over the 002 and 001, and it shows that this zinc oxide nanowire material is a single crystal and growth happened in a C-axis oriented. And further, we did some transmission electron microscopy analysis of single crystal nanowires. We see that our results are completely consistent with the FSM results. We find several hundreds of nanowires in disclosed on TEM grid, and the diameter is below 50 nanometers, and the single crystal, the lattice constant of the zinc oxide is 0.52, so it's completely matching with the user, and it shows the further single crystal nature of zinc oxide material, and growth happens in the CX oriented direction. And again, at the same time, we take a shot from a single nanowire to check the straightness along the axis, and we say that the most efficient nanowires below 50 nanometers, they are very straight and single crystal and consistent with the XRD examination. The sample we obtained at 24 hours, we did further some analysis like the Raman spectrum to see. We find a broad peak at 437 centimeter inverse. There's the characteristic of C6V symmetry, and the characteristic Raman spectrum, which was shown by the zinc oxide nanowires, broadening asymmetric Raman peak at this is a typical of zinc oxide Raman active branch, which is also a characteristic of zinc oxide nanoparticles. We further did to check the optical properties more. We did the room temperature PL spectra of single crystalline zinc oxide nanowires. This room temperature PL shows a suppressive peak at in the UV region, and a broad peak at a green region at 600, and another peak in the green region at 690 nanometers. So this may be due to some structural defects. And finally, I would like to conclude that this approach is in which we synthesize zinc oxide nanowires is a seedless template test and surfactant-free. We simply did a reaction using zinc salt, zinc nitrate, and HMT, and we obtained below 50 nanometers diameter zinc oxide nanowires. The SAD pattern is consistent with the XRD examination, and FESM is also consistent with the TEM observation. The nanowires show a good optical properties with less defects. This common strategy, simple process, fine quality, high yield, clean reaction makes this process more attractive. And I would like to say that simplest is the best. The future challenge is that the large-scale synthesis using this approach, a large-scale synthesis of this zinc oxide nanowires using the bottom-up approach to tailor the morphology, aspect ratio, and diameter of the nanowires, and application of these nanowires in devices, hydrogen storage, and photovoltaics, and other besides areas. The growth of these nanowires, this approach can be used to other metal chalcogenides like zinc sulfide and other cadmium sulfide and other materials. So, because the morphology tailored metal chalconide nanomaterials have a unique chemical, mechanical, electrical, optical, magnetic, and biological properties that is distinctly different from their macroscopic analogs. I would like to acknowledge the Brain Korea 21 project during the year 2005. Personally, I would like to acknowledge my lab, all lab mates, and my worthy professor due to its moral, intellectual, and
output.